Mars, actually, which is the only one that's out of view. Yeah, so that's, I should have switched them around a little bit. But no, I needed some decoration for the new office. I'd love to fill up the wall with a bunch of other fun stuff too, but I figured these are a pretty good backdrop for doing some space stuff.
Yeah,
although I do love
we're talking about Mars all night, so it's nice that you give a shout out to the other planets.
I'm with you. And actually, I will tell you, one of the questions I had for you is where you think other places in the solar system that we should be looking for life. Ooh. So I just, spoiler alert.
All right.
Dissipate that, yeah.
All right, so we're officially live. We've got folks still joining, so I'll give a few more minutes to get started. Before we do, since Ryan, you mentioned it, how do you feel about the current movement, Erin, of maybe we should stop looking at Mars and start looking at Venus?
Ooh, hard pass. I still think Mars is super cool. The information coming out of Venus is really exciting and definitely requires more thought and research, but so much time and effort has been dedicated to Mars, and I definitely don't want to get into a sunk cost fallacy, but there's so much cool stuff going on with Mars, which we're gonna touch on a little bit today. But there's just so many compelling reasons to keep kind of scratching that itch on Mars and keep looking, and we're so cool. And so many of the past rovers have just gotten us one step closer. And the way that I like to think of searching for life is it's such a monolithic problem. You kind of just have to keep breaking it up into these smaller and smaller questions. And we've been taking those steps on Mars for so long that it's like you can't stop now. And that means we have to sacrifice looking at any other planet. It's just we need more.
I remember when Mars was like
more people looking. So
I remember when Mars was like this thing of like, okay, well, we need to make sure there's water there. Is there water there? And now we're like, well, yeah, there's water. Is there life? Eventually.
And so the Perseverance rover, which is we were just talking about, it's I think 30% of its way to Mars. It's one of the first rovers in a really long time that's specifically dedicated to looking for signs of actual life. So the Curiosity rover was looking for evidence of habitability, so proving that it's worthwhile to actually look for life in these locations. But Perseverance is actually going to be dedicated to that problem as looking for evidence. And then the follow-up, the ExoMars rover, which has been delayed a few times, but ideally 2022, I think, is the new launch date. Fingers crossed, this will be the third attempt. But that one also is like actually dedicated to looking for these signs as this unambiguous evidence of life. And so that's what I get jazzed about.
You're right in the thick of it too, which is really exciting.
That's the dream.
It's an exciting time to be in that kind of research right now.
Yeah. I think it's an exciting time for anybody to be following it. Because like I was saying, these are the first kind of missions that are really dedicated to answering these questions and not, doing kind of all that preliminary science and developing the context of Mars and creating the case for why it's important to look for life in these locations and why it's reasonable and compelling and plausible is important. But now it's kind of like you're really getting into the meat of it, and you get to try to do the experiments that are going to be answering these questions or creating new questions, which is always exciting.
Mm-hmm. So it's now 8:05 and we've got 96 people here, so we'll get started. Yeah. we've been chatting. Sorry, everybody. So welcome everyone who's joining us tonight. Tonight is the Mars opposition, and we're super excited to be here. We are joined by a bunch of folks. We have our regulars from 3 different live streams that we have going on.
The Avengers.
The Avengers getting together. We have Chris Vaughn, who joins us for Insider's Guide to the Galaxy. We have Ryan, who joins us for our star parties. And we have John, who joins us for the Explore the Universe program. And then our guest of honor is Erin Gibbons. Erin's going to be speaking with us tonight. She's a PhD candidate at McGill University, and she's studying the possibility of microbial life on Mars. So it's going to be a really interesting talk tonight. I'm very excited to hear about your research and the background leading up to your research and everything. Along with researching the possibility of microbial life on Mars, Erin is also let me get it right, the Public Relations and Communications co-lead on the Space Generation Advisory Council, which I only learned about recently and I think is really cool. So I have some questions for you about that. And it aims to represent university students and young space professionals to the United Nations, space agencies, industry, and academia. So a very important role. And with no further ado, let me just briefly tell you guys about our structure tonight. So Erin's going to give us a talk a little bit about the possibility of microbial life on Mars and how we would go about looking for that sort of stuff. We're going to have a nice long Q&A. And so if you have any questions, we'll ask Erin then. I know Ryan is already chomping at the bit with questions, as he does. And then we're gonna go into a big section of observing and talking about observing. We've done our best to hedge our bets about live views on Mars tonight, with John in Halifax and Ryan and Chris separated by at least 50 kilometers, trying to get enough space. And so hopefully with any luck, Chris has clear weather and his telescope set up. So hoping, and Ryan can turn himself into Mars. So we've got lots of options. And so we're going to get some live views of Mars. We also have some recorded views of Mars from various different telescopes, so we can show you what the view looks like through different telescopes as well. We're going to talk about observing tips and imaging tips and all that good stuff after Erin's talk. With no further ado, Erin, I'm going to hand it over to you. And
Thank you.
Thank you so much for being here with us today. I'm looking forward to hearing about your research.
Well, thank you for the wonderful introduction and the chance to talk. This is so rad. I'm going to put my spectacles on so I can see you all. But I've been seeing the little chat bubble pop up with all these people introducing themselves, and I've seen lots of places in Canada, which is rad and what we expected. But I've seen a couple Australians joining in, so I am so stoked. St. Anne's Bay, Cape Breton. Oh, cool! I visited Cape Breton. So yeah, so stoked that so many people from across the world are tuning in tonight, and also so stoked that all of you are excited about Mars, excited about looking at Mars and learning about Mars. And because it's so nice to talk about Mars to people who are excited about it and who get jazzed as I do and these other folks do about exploring the red planet. So very excited to have a keen audience. So thank you all for tuning in. I'm going to start sharing my screen. Please somebody pipe up if it's not working. Ideally, you can see this now. Yes, beautiful. I got one thumbs up at least. Perfect. I'm just going to move all your faces out of the way so I can see my own slides. All righty. So as you all know, because you're tuning in, this evening is all about Mars, our wonderful red planet in the sky, which if any of you have been able to take a peek at the planet in the last couple of days on some of these clear nights, you can really start to see that kind of orange coloring. And later, we're going to be to some great views of the planet, making some videos. And Jenna's lined up these great seminars about observation and imaging, which I'm quite stoked to tune into soon. But I have the pleasure of kicking off this evening of Mars Mania. And I wanted to start off kind of with a discussion about why we care about Mars. So why Mars is the subject of so many experiments and so many exploration efforts, and why I and many others choose to dedicate their careers and probably more than enough of their free time to studying it. So one of the reasons, particularly one of the main reasons that motivates me for the exploration of Mars, is the search for life. And so this is the quest to answer this very fundamental question of whether or not we are alone in the universe, or if there is some other form of life out there beyond the planet that we know and love and call home. And Mars, it's a really tantalizing target to try to address some of these core questions about who we are and what it means to be alive. And we'll get into some of those reasons in a little bit. We'll delve into that. But one of the other reasons that's often overlooked is just that Mars is so close. I mean, we can see it with just our naked eyes from our backyard. And that makes it so much more feasible to study and to test hypotheses and to iterate on our theories. So you may hear in the news about hundreds and thousands of exoplanets being discovered, and how astronomers are really honing in on some of these Earth twins that are scattered throughout the universe. And these are really exciting as potential places that life could survive. But frankly, we're not going to be able to visit those places anytime soon. Mars is really within our reach, and it makes exploration so much more thrilling, for me at least, when you can actually see photographs and real-time data coming back from that place that you're exploring. So the photo that I've picked for my title slide here, this is one of my favorite images that has come out of the Curiosity rover mission that's currently roving around on Mars today, because it really just shows, I think, how accessible Mars is. We have a rover right there on the surface taking these incredibly crisp, beautiful photos of a surface that is kind of recognizable. Like, it doesn't look that wildly alien. We can see rolling hills, we can see layers of sand and dirt, we can see valleys, we can see some mountains in the background. This one has been color corrected to give it kind of an earth-colored sky, but this really doesn't look like a wildly alien place. And it gives me hope, at least, that it could have been a haven for life as we know it. Now, I've put a question mark next to this statement of life on Mars, question mark, because although these photos look almost Earth-like, and although decades and decades of work have revealed pretty compelling evidence that point towards at least the plausibility of life having emerged on Mars, we have yet to find any unambiguous evidence of life ever having lived there, either past or present. And this doesn't mean that life isn't there. It just means that the evidence may be elusive. But we were discussing this before some of you joined the call. We're living in a very exciting time because in the very near future, just in February, actually, February 2021 of the new year, NASA will be landing their newest rover on the surface of Mars. And this rover, Perseverance, is specifically dedicated to seek signs of ancient life. So it's specifically designed to look for these elusive signs of life and start answering these questions of, did life ever exist on Mars? Now, before I move forward, one challenge I want to highlight here is that searching for life on another planet with remote controlled rovers, it's really hard. These missions, they're extremely complex. Oops. Are you still, yes, okay, sorry, still seeing my screen. These missions are really complex, and realistically, we can only send a few of these rovers because they're quite expensive to explore Mars. And that means that with our rover missions, we only have access to really a tiny, tiny, tiny fraction of the planet. And so this is where Curiosity is landed right now in Gale Crater. And Curiosity, it's been exploring Gale for 8 years now, since 2012. And Curiosity, it's the most sophisticated mobile remote controlled laboratory that humanity has ever flung across the vacuum of space and landed on another planet. And yet, even with all that science behind it, it's only explored less than 0.001% of the surface of Mars in this whole 8-year time span that it's been roving around on the surface. And so what I hope this makes it clear to you is that if we have any hope of finding signs of alien life on this entire planetary surface, it's absolutely crucial that we send our rovers to the best possible locations, to the sites that we really think is the best possibility of retaining evidence of life that could have existed there. And so one of the questions that kind of drives planetary science is, where do we begin? How do we narrow down this seemingly infinite set of possibilities for life on Mars? And it turns out that a pretty good place to start is just asking when. So when could life have existed on Mars? And when in its history was it perhaps most abundant? And answering these questions will give us, one, it'll help us pick locations that correspond to these time periods of likely habitation on the surface of Mars. And it will also give us some insight into what kind of life may have had time to evolve on the Martian surface. And that'll give us a better indication of what kind of evidence for life we should be looking for, and will give us insight in how we could optimize our rovers to kind of look for that evidence and make a successful discovery. And so today in this discussion, what I really want to spend time doing is breaking down a little bit of this concept of when. So I want to walk you through a brief history of Mars, all the way from its planetary formation to the dusty, dry, cold planet that we know and love and hopefully get to take a peek at today. So that you can have a better understanding of what we think life on Mars could have looked like and when it could have existed, and then how scientists take this information and translate it into hypotheses about where to look for life and what kind of evidence we are actually looking for. So to begin, we will start at the beginning. So if we go all the way back to the very beginning, we do think Mars formed along with the other planets in the solar system about 4.6 billion years ago. Relatively little is known about the earliest few million years of Mars's history, because much of the evidence has been lost to time. This is a very long time ago. But scientists do generally think that the planet endured an extremely high rate of meteorite impacts in its early stages. You see, in the early years of the solar system was quite a different place than we have today. There's many more asteroids and protoplanets flying around, and Mars was just constantly being battered by debris that was flying through space. And this damage probably made it really difficult for any life to gain kind of a proper foothold on the surface. We're talking, planetary scale sterilizing impact events. But this period of time is still, it's important to think about when we think about the grand scheme or the overall concept of life on Mars, because comet and asteroid impacts during this period may have actually helped deliver water to the surface of Mars. And we generally think of water as an essential ingredient to life as we know it. Now, the surface of Mars was extremely hot at this very early point in its history, which I tried to give you some indication of with this image here. And it was quite hot because planetary formation, that process, and these processes of impacts, They generate a lot of heat, it melts all the rock. So Mars was quite warm at this period, during this period. So the water that was being delivered by these comets and asteroids likely existed as a vapor in the atmosphere. But slowly with time, this water would have cooled and condensed, perhaps forming lakes, maybe even oceans of liquid water at the surface. And this may have opened kind of the first window of opportunity for life to emerge on Mars. However, like I mentioned, we do have very little evidence of life, very little evidence of anything of Mars from this period of time. So yeah, not much evidence left here today, which makes it very difficult to study. We do have better evidence of the slightly later periods when conditions on Mars were a bit more stable, a bit more amenable to being preserved and fossilized. Excuse me. And we typically divide this period of time into kind of three main geologic periods, which are important to discuss when we're thinking about life on Mars. And so if we draw out this timeline of Mars and Earth too, for good measure, and we'll get back to that. Today is kind of on the right. This is the present day here, and formation about 4.6 billion years ago is all the way here on the left. And this is a billion-year time scale. And so you can see that the main geologic eras of Mars are generally divided into three periods, starting with the Noachian about 4.2-ish billion years ago, moving into the Hesperian, and then the Amazonian. And while you may not have heard kind of these official names of these eras in Mars's history, you've probably heard about these time periods discussed in some way, just through natural discussions of Mars. So the Noachian, this very early period of Mars's history, is probably the time period you hear somebody say that it was warm and wet. Now, even today on Earth, where a lot more science is being done, scientists disagree about how the climate has changed and modified Earth through the past, and it is an unbelievably monolithic task to try to understand the climate of Mars 4 billion years ago. And so scientists still debate whether this period was actually warm. This is questionable. So if you do want to see scientists argue, just go to an early Mars conference and ask what the climate of Mars was like in the Noachian. So yeah, warm, quite questionable, but it is generally agreed upon that it was in fact wet. And this is because the ancient rocks that are preserved from this Noachian era, they preserve evidence of ancient water flow, or that's how we interpret it. So we see these valley networks, which look very similar to the extensive river drainage basins that we have here on Earth. We also see these massive canyons that have been carved into these rock faces, which could have been formed by raging rivers traveling across the surface. We also see these features which look quite a bit like delta deposits. And this is where water that was rushing in a river would have suddenly met a standing body of water, so a lake or a sea, and dumped out its sediment load. We also see this great picture again from the Curiosity rover. And this is showing some rounded pebbles. And these may have been rounded by the flowing of an ancient river, which kind of smooths those pebbles out over time. And we also see evidence for what's called clay minerals. These have a special place in my heart. I studied these in my master's degree. And clay minerals are they're a special type of mineral that fundamentally require water to form. And we find these minerals widespread across the Martian surface. And all of this together, these feature in these mineralogical clays, they all add up to just pretty compelling evidence that water once flowed across Mars during this ancient Noachian era. And what this tells us is that the atmosphere was probably much thicker on Mars than it is today, insulating and kind of protecting the planet from the vacuum of space and allowing water to be stable at the surface. And it's at this time that we really think Mars was probably the most Earth-like. It may have even had a water cycle that maintained kind of subsurface aquifers that recharged lakes and seas that would then evaporate and form cloudy skies that may have precipitated as rain and snow. So this is really that Earth-like time of Mars's history. And the key takeaway here is that this time period, this Earth-like time period on Mars, corresponds to the, so we're looking at the Noachian here, and this corresponds to the Hadean and Archean eras on Earth. And this is when we think that life actually evolved on Earth. So our earliest confirmed fossils are from about 3.5 billion years ago, and these were found in Australia. So shout out to our Australian viewers. I saw some of you in the chat. And if we look at isotopic evidence of life, So these are chemical fossils, and they're actually found right here in Canada on the East Coast, I believe. That pushes the date for this potential origin of life about 3.95 billion years ago. Although this evidence it's still under debate, it's quite recent, so lots to look into if you're interested. And so the thinking goes that if life appeared kind of during this ancient period that corresponds to the Noachian, it may have showed up on Mars as well, right? Like if life could happen here, why not on Mars during this Earth-like period? However, this oasis state that we just discussed on Mars with lakes and seas and cloudy skies, it was short-lived. You see, disaster was kind of brewing throughout the Noachian inside of Mars because Mars was slowly losing its atmosphere. So this chart that I've thrown up on the bottom here, this is just a line that kind of depicts the thickness of Mars's atmosphere through time. And we see that it starts steadily declining in the early Noachian and continuing that decline into the Amazonian. We don't fully understand what caused Mars to start losing its atmosphere. And scientists think that there was actually several complementary processes at play that could have had an impact on this erosion of the atmosphere. But one of the leading causes that is thought to have definitely contributed to this erosion of the atmosphere is called sputtering by solar wind. Excuse me. And the solar wind is essentially, it's just a stream of extremely high energy, very fast moving charged particles that are emitted by our sun. And it just floods over our entire solar system, flooding over the planets. And on Earth, we're lucky enough to have a magnetic field. And this protects our atmosphere by deflecting these particles away. But Mars, it lost its magnetic field pretty quickly after it formed. And without a magnetic field to protect it, the solar wind, it essentially crashes into the molecules in Mars's atmosphere and bumps them out into space. And this process has been going on for millions and millions of years, slowly chipping away at that atmosphere, just making it thinner and thinner and thinner. And so at about 3.5, 3.6 billion years ago, this period just here, most of the atmosphere has been stripped away from Mars. And this is when we really start seeing very tangible evidence for a dramatic climate change that really altered the surface of Mars. And this is known as the global transition, very creative name by the scientific community. And it fundamentally marks the beginning of the next era of Mars's history that we're going to talk about. So this is the Hesperian. Hesperian is quite an exciting time in Mars's history. It's short-lived. It's an intermediate kind of transitional period. And this is really the phase at which Mars begins going from the warm, maybe warmer, wetter period of the Noachian to the kind of dry, cold, dusty planet of today. And so, as I mentioned, this global climate change was initiated in part by the loss of the atmosphere. Without that atmosphere to really kind of keep heat in, the temperature of Mars dropped significantly, well below freezing. The atmospheric pressure was also dropping, and it fell below what we call the triple point of water. And this is just the triple point of water. It's the lowest pressure at which water is stable as a liquid. So under these new conditions, liquid water was no longer stable, and it would just boil instantaneously at the surface of Mars, even at freezing temperatures. And so Mars starts losing much of its water directly into space. And so it's during this period that, we say goodbye to the lakes and seas, so long to the raging rivers, and farewell to the moist soils of the Noachian era, and hello to this kind of frozen, arid desert. However, not quite all of the water has evaporated from the Martian surface. But with these persistently colder temperatures and lower pressures, much of the water that is able to survive on the Martian surface, it probably changed state. So becoming either retreating into the subsurface and becoming kind of this very thick permafrost layer, or if it maintained at the surface, it was probably becoming glaciers and ice caps. And some researchers refer to this period as a Snowball Mars. And this is just when the surface of Mars kind of becomes nearly or entirely frozen. It's thought that the conditions on Mars may have looked similar to what's encountered in the polar environments on Earth. So that's why I put this picture up here, just to give this kind of a sense of what Mars may have been looking at like at this time, with exposed rock and glaciers. However, unlike the polar regions of Earth, this Hesperian age on Mars was also a period of massive volcanism and tectonic activity. So during the Hesperian, all of the large shield volcanoes, they had already begun to form on Mars. This includes Olympus Mons, which I suspect some of you may have heard of. It's Mars's biggest volcano. It's also one of the largest volcanoes in our entire solar system, and it is the largest planetary mountain. To give you a sense of scale, this volcano has a base about the size of France, and it is 2.5 times as tall as Mount Everest. So an absolutely huge volcano. And Olympus Mons and other volcanoes, they were releasing these incredible amounts of molten lava that just flooded the surface of Mars. And these floods, they were expansive enough to resurface, it's estimated about 30% of the entire planetary surface with fresh volcanic rock during this period. I want to just pause and have everybody imagine what 30% of a planet being covered in fresh lava would look like. So on Earth, about 30% of our surface is covered by continents, not even quite 30%, I think it's about 29, and the rest is oceans. So if our planet, if Earth was 30% of Earth was covered with lava, that would be our entire continental landmass being covered in molten rock. It's just a huge amount of lava flowing across Mars during this period of history. It's wild. But keep in mind, the last slide we were just looking at Mars may have looked kind of like these polar regions on Earth with glaciers and permafrost. And so this massive amount of heat was then interacting with those icy bodies. And these volcanoes, they would have melted some of that permafrost or some of the ice at the surface and then caused catastrophic floods of meltwater. And so we're talking thousands of Mississippi rivers worth of water flowing across the surface at once. And so if this cycle of huge planetary scale lava floods followed by catastrophic water floods isn't kind of apocalyptic enough, keep in mind that the water floods were probably acidic. And this is because the volcanoes, they're pumping out lots of sulfuric dioxide and other volcanic gases, which are then reacting with any residual water and ice on the surface to then form sulfuric acid. And so life in the Hesperian, it would have been, life as we understand it at least, would have been really tough, right? The surface, it's drying up, it's freezing, it's acidifying, it's becoming increasingly exposed to radiation as that atmosphere gets thinner and thinner. So any life that could have existed on the surface was probably just fighting to survive. It was probably retreating to any kind of isolated, protected niche that it could find to hide from this hostility that was developing at the surface. And this, I'll admit, this is a picture of Iceland, but this is one of the places on Earth where we see volcanoes and ice interacting. So I thought it was a nice representation of potentially what we're seeing in the Hesperian. And so as astrobiologists, getting back to Mars, we often think about the habitability of Mars as degrading throughout the Hesperian. So it's this state of degraded habitability. And eventually, as we move forward with time, this process continues. Most of the water is lost. The volcanic eruptions eventually begin to slow down, become less frequent. And this is, as the Hesperian comes to an end, we enter the third period of Mars's history, which is the Amazonian. This is the longest period of Mars's past, and it is the state of Mars that we know today. And frankly, the Amazonian, it's relatively boring compared to our periods of flowing water and volcanoes and floods and acid of the past. This period is generally, it's characterized by a relative absence of large-scale geological or climatic change. Conditions seem to have settled into a relatively steady state on the surface of Mars. So today, the atmosphere is so thin that, again, pure water just instantly vaporizes. It boils at the surface. Temperatures are extremely cold. They dip down to about negative 200 degrees Celsius. The average is about negative 60 degrees, very cold. And the surface is absolutely bathed in radiation. So it's commonly described as a frozen desert. It's a totally hostile landscape, very dusty. And this is the state of Mars that we are currently exploring. But it's not necessarily the state of Mars that we're looking for life within. So how does this brief history of Mars that we've flown through about 4.5 billion years of planetary history in 20 minutes. So how does this help us kind of contextualize our search for life on Mars? Well, it gives us insight into this question that we started with, which is when could life have existed on Mars? So this history of Mars, it tells us that conditions at the surface today are pretty hostile. And this is consistent with the fact that we're really not seeing any obvious evidence of life, especially not roaming around the surface of Mars today. We don't see large complex life forms marching about. It's simply not a habitable environment to life as we understand it. And we also see that these hostile conditions that we see today, they're not new. In fact, Mars has been relatively unfriendly towards life for about the last 3.5 billion years of its history, so most of its life. And life forms, again, as we understand them, probably would not have been able to survive or really thrive in these harsh settings. So it doesn't make sense to send a planetary mission to look for signs of life in surface environments that correspond to these periods of time. This is not to say that life couldn't, be fighting to survive during these kind of later periods or even today, but it's probably not abundant or widespread, which makes it kind of a poor or a less compelling target to look for evidence of life, especially under the limitations that are imposed by a rover mission that can only access, again, that very small area of the surface. It makes more sense to focus our efforts to this Noachian era, where Mars still had an atmosphere, where we see evidence for this abundant, potentially abundant flowing water at the surface, and where conditions were favorable to life as we understand it. It seems most reasonable to assume that if life existed on Mars, it would have been most successful during this kind of short window deep in the past. And so if we ask, where should we look for life on Mars? The obvious answer kind of becomes, well, we should look for signs of life in environments that correspond to this Noachian period. So we're going to look for environments that are preserved from about 4.1 to 3.5 billion years ago. And given this ancient age of the Noachian and kind of the lack of continuous habitability since then, our search for life on Mars can almost be thought of as a search for fossils of life on Mars. And so this history of Mars that we've flown through again, it gives us one other important lesson, and that's insight into what kind of fossils we should be looking for. So when we think of fossil evidence of life on Earth, what may come to mind is dinosaur bones or fish bones or exoskeletons or even fossilized plants. But these are not generally the targets of missions to Mars. It's quite unlikely that large animals or complex life forms with differentiated tissues probably ever evolved on Mars. These types of animals that form skeletons that get preserved as bones on Earth, they didn't evolve even on Earth until relatively late in our history, just about 500 million years ago. And this is way long after Mars kind of degraded into this frozen desert surface. So we really don't expect that these types of life would have ever managed to evolve on Mars. And so if by this kind of same line of thinking, if we turn back the clock on Earth and we look at the type of life that was maybe existing in this ancient period, we see that life forms were very simple. So simple that they couldn't even perform photosynthesis. Photosynthesis evolved much later. Instead, these very early organisms, they were making their energy from the chemicals in rocks. In a very simplified sense, they were kind of eating rocks to gain energy. And as you may imagine, eating rocks is not the most efficient form of extracting energy from your environment. So these organisms, they couldn't grow very large. They were quite stunted in their growth. They remained quite small, about on the scale of viruses today, which is about 0.001% the width of a human hair. So really tiny, tiny life forms existing on this very early Earth. And this is the type of life that, again, it's existing that same period of time that we think Mars is habitable. So this might be the type of life that populated Mars during this early window of habitability. And so essentially on Mars, we are looking for traces of microbes, like the bacteria or archaea, these very ancient life forms on Earth. And these are fundamentally very, very tiny forms of life. They don't produce physical body fossils that are very easy to find. You need a microscope. However, sometimes they do leave behind these characteristic structures in the dirt or soil that can become fossilized, and those are easier to see. And so that can be a sign of life that we're looking for on Mars. And another kind of fossil, so not a body fossil, not a bone or a fossilized tissue, that we can look for on Mars is a chemical fossil. You see, life, it produces these unique chemical compounds from its biological processes, and these molecules can be preserved in rocks similar to bones and tissues. And so it's much easier to perform chemistry experiments on the surface of Mars and look for these kind of special biological molecules than it is to look for these microscopic body fossils. And so a lot of effort today in searching for life on Mars is searching for these chemical fossils in ancient rocks. And I'm not going to get into it, but this is actually fundamentally what my PhD is dedicated to. It's trying to understand what these chemical fossils would look like in Mars-like environments here on Earth. And so this brings me to the end of my presentation. I hope that I've given you a bit of a better impression about what it means to search for life on Mars. I hope you have a better understanding of how scientists kind of approach these questions and think about these problems. And also that you appreciate that these types of questions, they need a lot of support from different types of experts. So fundamentally, searching for life on Mars is multidisciplinary. It's a joint effort amongst biologists, geologists, climatologists, physicists, chemists, and so many more. So to all the students on the line, or young professionals, or space enthusiasts, or anybody who's looking to maybe break into this field, just know that you and your expertise will be so valued. There is so much need for just creative inputs to this field. So if you have any interest in the search for life on Mars or Mars science in general, just know that there's a place for you in space. And on that note, I want to take just a few more minutes of your time at the end of my presentation, again, to just speak directly to students and young professionals on the line. As Jenna mentioned, I'm a member of the Space Generation Advisory Council. And this is an organization that really helped me kind of find my place in the sector and meet like-minded individuals and just get excited. So I'd love to just introduce you a little bit to the organization and some of the opportunities that it could have for students. And this is not exclusive to Canadians. This is an international organization that kind of represents the voice of students and young professionals, that specifically youth between the ages of 18 and 35, to the United Nations. And it's dedicated to maintaining the sustainable and fair uses of outer space. And the idea is that our generation, we are going to be the leaders of space tomorrow. And so our voice should be represented in policies that are created today and will be affecting us when we are in the workplace. And so fundamentally, the purpose of the SGAC is it's an international group that it's meant to create this community of like-minded enthusiasts, people who are enthusiastic and excited about space, connect that community to peers and mentors and professionals within the industry and governmental positions related to space, as well as providing kind of experiential, and leadership opportunities for these young leaders in order to enhance their career experience and also represent their voice to the space sector on a global stage. So the SGAC, it has a huge network. We're active in all 6 regions, or 6 of the regions recognized by the United Nations. We have over 15,000 members across 150 countries. So there's definitely probably people around you. There's national points of contact in all of these highlighted countries that you can reach out to and get more information. Membership is totally free, and there's no obligation, no commitment. You sound like a commercial. But it's just, and if you become a member, you have access to kind of our 5 pillars of growth. So we organize events regularly. We have project research groups, so you can fundamentally get involved in research in the space sector. We have opportunities for mentorship and professional development. We offer scholarships. I think we gave out about 150 scholarships in the last 3 years. And you can also directly be involved in activities related to the United Nations and the sustainable use of the space sector. So if you guys want any more information about that, please feel free to ask. But beyond that, I'm also very happy to answer any questions about Mars, search for microbial life, upcoming missions, Iceland, because that's where ideally I will be searching for little microbes soon enough, as soon as the borders become a little bit more open. So yeah, happy to chat about Mars.
Thank you so much, Erin. I really appreciate the time that you took to tell us about all of that. And I've never heard an in-depth history of Mars as a planet before. So that was fascinating. Like,
I know it's so often gets truncated to, it was warm and wet in the past, and that doesn't do it justice because it's so cool.
That's so cool. Like, I feel like I was watching a National Geographic movie about about the time period. There's a couple. So if anyone has questions, please do ask them in a Q&A right now or in the YouTube chat, and I will compile them.
Do you want me to stop sharing my screen? Sorry.
Yeah, sure. Unless you have something relevant, maybe share it again when it's relevant, so then we can see your face a little bit better. Perfect. Okay. I think we're all going to be asking questions here and there because I know Ryan's chomping at the bit. I think we're all really excited about it.
Again, I love talking about space, and I'm so jazzed just to have an excited audience. I've just been, spewing all of this information to my parents all summer, and they can only pretend
captive
to be
audience. Now you have more audience. That's right. Excellent.
It's nice. It's nice to have other people to virtually talk to about the stuff that's going on. I have questions, but I think Ryan, do you want the honors of asking the first question?
I would really be honored. That was a fantastic talk, Erin. Thank you for that. And your stuff with the SGAC. I've got a few questions about that as well. But I'm going to start with one that I've been wanting to ask ever since I read a bit of your background research. Was Martian meteorites, right? There's been impacts on Mars that have kicked up material, and that some of that material has made its way to Earth. So we actually have Martian meteorites here on Earth. Have any of those been from the Noachian period, or have those contributed anything to our knowledge of whether there might have been more conducive environments for life in the history of Mars?
I think they've contributed to the confusion. Some people on the line might be aware of, there was some past potential discoveries of microbes preserved in these Martian meteorites. So there's tons of press releases coming out. We found life on Mars. We found microbial evidence in these meteorites. And it later, scientists at the time followed up and tried to confirm this evidence, and the evidence really wasn't there. And they couldn't confirm this unambiguous sign of life in those meteorites. So haven't confirmed. In terms of whether we have meteorites from the Noachian, I don't actually know. But one of the problems with using meteorite material from Mars is that we have no way of telling where on the planet it came from. So there's kind of no geological context to that material, which makes it really hard to place any of those discoveries that we make about that meteorite or in the context of this Martian history. Again, we have 4.5 billion years of history of Mars, and trying to place that meteorite in kind of its place and time on Mars gets really difficult if you don't know where it came from. And so that's why it's really exciting. The next rover, the Perseverance rover, is going to be able to drill in to the rock, collect samples, and ideally those will be brought back to Earth. And that's cool because we can catalog exactly where they came from on the planet, when, and then when they're back on Earth, we have the ability to subject them to all our high resolution analyses in the labs here on Earth, and we can date them and look for all the signs of life we could want.
Amazing, thank you.
I'm going to say, so I know Chris is a planetary geologist as well. So I'm going to assume, Chris, that you have harder questions. So John, do you have any questions, as I know you're also an expert, but maybe like on a slightly less expert level?
Softballs, John, softballs.
I write books targeted at 10-year-olds. So that's about my level right now. This was absolutely fantastic, Erin. I'm like dreams are dashed now, knowing that it took like 3 billion years to form sort of the first fossils on Earth, but that Mars only had, life, the possibility of life during that first, billion in the Noachian period. So I always dreamed of finding that first, going to Mars someday as an old man and finding that fossil and becoming famous.
Finding those Martian dinosaur bones.
Yeah, my dream is now dashed. I guess my question is, if you were to go on, to Mars someday and be there in person, what specifically would you be looking for that would be different from what a rover would?
Ooh, that is a good question. I think what the real value of having people, like boots on the ground, human beings, is just how much more land we can cover. So I think the Curiosity rover, what I was trying to get at a little bit in the beginning, it's covered about, I forget the exact number. It's a little more than 20 kilometers, I believe, in its total 8-year exploration of Mars. And I'm like, I can hike 20 kilometers in a weekend. So if you had this team of keen geologists on Mars, they could just cover so much more ground and do so many more analyses in the time it takes a rover to just explore these small amounts of space. So I don't actually know what I would look for specifically. I think I would just go out day after day and cover more ground.
Dig deeper, I guess, huh?
Yeah.
Bring a bigger shovel.
Yeah. Take a shovel, drill.
Chris, do you have any questions?
Yeah, so I was going to ask, how do we know, presumably then we want to search for life where the rocks on the surface are of the Noachian period, and how do we know which parts of Mars are of that age?
That is a super good question. And it is difficult to date the surface of Mars, especially without having these samples kind of back on Earth where we can do high resolution isotopic analyses. That's often how we date rocks on Earth, is doing these radiometric ages. I'm going to share my screen one more time because I do have a slide that shows something a little bit helpful maybe for that discussion. Instead of doing kind of direct dating on Mars, so looking at these isotopic ages, we often do what is called crater counting. And we have some understanding of how often these planets in the solar system were getting inundated by impacts throughout time. And so if you just count how many craters are preserved on the surface, that density of crater that you see preserved today will give you some sense of how old that material is. So in this kind of the warmer colored, so just to give some context, this is an elevation map of Mars. So the warmer colors are higher in elevation and the cooler colors are lower in elevation. And you see in these highlands, so the southern highlands, you see way more craters. And this tells us that this is a much older, much more ancient terrain. Whereas the northern part of Mars has been resurfaced, and this is potentially resurfaced by lava flows, resurfaced by water, by erosion. So these are these rocks have been modified by younger geological processes, whereas these rocks in the southern highlands, they're telling us that they're preserved from this very ancient period when Mars was being inundated by meteorite impacts, and that density gives us some sense of an age. And so we can begin to understand kind of relatively which rocks are older on Mars and have some idea of how long ago they were forming. So that's one of the tools in kind of the planetary geologist's toolbox for dating rocks on Mars, is this idea of crater counting.
Can you show on this map, point out the Jezero crater site? It's up there near the Isidis Basin. Yeah.
I can, yeah, it's right in here. And my previous, so yeah, the Perseverance rover, that's a great question, Chris. The Perseverance rover is going to be landing in Jezero crater. And so that is, oops, where's my arrow? Just here. So part of these kind of, Noachian age rocks, but in a bit of a lower region, and that makes it a bit easier to land a rover. So this is that Jezero crater area, and this is, yeah, right on the edge of that basin.
Can I sneak in one more question?
Absolutely.
Sure.
I'll go back to the map for a second. So I've always wondered whether anybody believes that the impact that created the Hellas Basin may have triggered the volcanoes on the opposite side of the planet. Do we know if the ages match up?
That is a good question. Hi, that is not something I know. But yeah, that's an interesting question. But yeah, the whole map of Mars is just exciting. But no, I don't know the answer to that one.
No problem.
It is a cool question. It'd be very cool. We have lots of questions from folks watching, so I'm going to try to lump them into Mars questions and then space policy questions, because we have a little bit of both. What would you like to start with?
Ooh, let's switch it up. Let's do some policy questions.
Okie dokie. Can I ask mine first then?
Absolutely.
So what issue are you personally most concerned about being addressed, or do you think should be most urgently addressed when it comes to space policy?
I'm going to say freedom of information, like equitable sharing of information. Especially as we move forward and more nations are getting involved in the exploration of space, there's kind of this idea that people want to kind of keep that information proprietary to themselves, and that makes sense, because if you're the nation or you're the entity, the state that's putting in all the information to putting that mission together and getting that information, you kind of want to keep it and have that primary research for yourself. But I think space exploration, it's so much bigger than the boundaries that we've placed on our own planet, and it really is something that and what's cool about space to me is that it's kind of universally exciting. It galvanizes people together. It's exciting to look up at the stars. It's exciting to get Mars or information back from Mars. And I think that information, regardless of who collects it, should just be equitable and accessible to other people so that they can get excited about space, excited about planetary exploration, and want to pursue careers or hobbies in science and technology and engineering and math. And I think space is such a good way to get people excited about these topics. And I think it should be shared more openly, especially moving forward as these different parties are getting involved. So I'd like to see some sort of, maybe not regulation, but recommendations or like an agreement that this type of information is just shared.
That is an excellent answer. Thank you for sharing. Now to questions where I don't know the background. So I might need you to explain some things. I don't know what the Artemis Accords are, but someone has asked, what do you have any comments or reflections of the Artemis Accords on the future of Mars missions?
I do not. It's a good and timely question, and it's unfortunate that I can't answer it as well as I would like to at the moment. I am through the SGAC. I'm involved in this action team for understanding kind of the regulation, for defining regulations, especially from the youth and young professional perspective of how space exploration on the moon should be operated in the coming years. And so we're having a lot of active discussions in this group about the Artemis Accords and other kind of potential regulations that are coming out of other countries. And to be honest, I have not delved as deeply into them as I should. We're preparing for a couple really big sessions with leaders of states in the coming weeks. So I'm going to dive into that more. So I'd be able to give you a better answer in a couple of weeks and not right now, but yeah, apologies for that. But yes, very exciting times. And there are student groups related to that in the SGAC. So that if that is something you're excited about, join us, join our cool action groups.
Yeah, that's the way to keep informed about it. And can I plug, do you have social media to plug about where you share information like this?
For SGAC? Oh gosh, yes. I run the social media accounts for SGAC.
Of course you do, yeah.
Follow me at SGAC. Yeah, so we're on Twitter, Space Generation Advisory Council. That's probably our most active platform. We have a global page on Facebook. We also have 6 regional pages. So you can find the North American SGAC page, the European SGAC page, Asia Pacific, African, et cetera, et cetera. So you can find one related to your specific area. We're also on LinkedIn. We are on Instagram. And there's also, again, like what I was trying to say is we do have national points of contact in most of the countries that we're active in. So if you want to connect specifically with a person who's in your local region, reach out and I can get you that contact information, or you can look it up online. We have a website, but there is probably somebody embedded in the SGAC who's very nearby you and has a better perspective of what we're doing kind of on the ground in your area.
Are there a lot of people at university campuses?
Not specifically necessarily embedded in the university campus. We don't generally have university groups associated with the SGAC. It's much more on an individual basis. Okay. But yeah, you can reach out to those specific points of contact.
Awesome. Okay, so we have a question from Kate. If a space agency were to send people to Mars, do you think they would claim it for their country? For example, the US put a USA flag on the moon when they landed. Do you think this would actually affect international laws, diplomacy, and jurisdiction?
I think it would cause a problem. As I understand it, you can't claim, don't quote me on this, you can't make land claims in space. That's as I currently understand it, but there is a lot to be done with regulating these planetary surfaces or just celestial bodies in the solar system in general to kind of nail down what exactly those rules are, and then getting internationally people to agree to them. So I think that would cause a huge amount of problems, especially because the access to space is not equal across nations. You know, there's certain nations that have the technology to access space that other nations just do not. And so if those bodies and states were making a claim that other people just don't have the capacity or like don't have an equitable box to stand on, it's unfair. And there are discussions and regulations that need to be happening as we start exploring and having a more regular presence of humanity in space.
Mm-hmm. It's almost, I mean, it's tricky to even I don't know, I'm nervous saying this on a live feed, but even having the US plant a flag on the moon, that negates all of the contributions from other countries that got them there as well. So yeah, it'd be nice if we acted more as a team.
It's important to have these discussions now, because when this explodes may be a bad word, but when this grows exponentially,
blossoms.
Space tourism, more travel, more exploration, more countries exploring as well. We're going to need those regulations to guide a lot of that new exploration. So it's good to have those conversations now.
Mm-hmm.
Yeah. And I see in the chat very quickly some saying it's a little unfair. I can't even apply to NASA because I'm not a US citizen. You're right. You can't be an employee of NASA, again, as I understand it, unless you're a US citizen. But there are other ways to get involved there. Again, there's other nations that are involved in the space sector. That's not just NASA. And there are ways to collaborate with NASA as a foreign national. So for example, I'm Canadian and I collaborate with NASA. It's just, there are other ways to get your feet into the space sector and open those doors for yourself. So don't limit yourself just with your nationality. There's so many opportunities for people across the globe to access space, and this is a great time, especially that we live in the area of communication. So just reach out, find a network, connect to people connect to like-minded individuals, and they're going to be able to open those doors and find those connections for you in your area. So don't.
It also doesn't always look like NASA, right? Like you can do things like satellites and other ways you can do a lot of research about other planets using the Earth as a model in some cases too. As you say, going to Iceland to do research on microbial.
And it doesn't have to be NASA, but NASA is also fundamentally very open to collaborations. I mean, I've interacted with NASA several times in the past, and they've been, I'm not a US citizen, so they've been very open to collaborations, and all these space missions that they're sending. So the Curiosity rover, the Perseverance rover, it's not an America-centric mission. I mean, there's the team that I work on it's American, French, and Spanish. And so that when we have our telecons, it's kind of ridiculous trying to organize them because nobody's in the same time zone. So it's a huge international effort. So yeah, please don't feel limited by your status as a
US citizen. Yeah. Okay, last question about space policy, and then we'll jump into a few Mars related questions, and then we're going to get to actually viewing. How do you feel about space pollution? And this, literally the question from Warren is just space pollution, but this matters a lot to astronomers because, of course, I mean, partially because satellites go up into space and they end up showing up in pictures and they end up showing up in research and that sort of stuff. And eventually they all kind of end up becoming space pollution. What do you think about it?
Well, I mean, when you first said space pollution, I didn't even think there's a barrier to observation if you have, there's this whole discussion of like this Starlink satellite array that's going up and how that's going to really damage our views of the night sky, and it's going to affect astronomers who want to be making these observations. So there's that degree of pollution just of our view shed. Where my mind immediately went when you said space pollution is just the amount of debris that we have encasing our planet. It is becoming a point of discussion of when you launch, how do you launch through this kind of haze of space garbage? And again, that's not something I specialize in. I'm much more on the ground. I deal with geology and microbes. I'm not in the launching phase or trying to steer the rover through this haze of planetary debris. But it's a very prominent question that's coming up, especially as more entities are trying to launch satellites. It's filling up that space, and kind of the common practice right now is when a satellite depreciates, there's no method of bringing it back down to Earth or getting it out of orbit. And it kind of just dies and decays and remains in this space around our planet. And so there is option, and I've been to conferences that kind of discuss that there is a need and there's a niche, there's a space that should be filled by these companies who are going up to maybe clean that space, or to there's also discussion of making satellites more reusable or what's that word? Chargeable or
replenished.
Yeah,
replenished.
Replenish. What's the
Refuel.
That's the word.
Serviceable. Yeah.
Serviceable. So when a satellite expires, you could go up and fix it rather than just letting it die, decay, becoming a piece of debris, and then replacing it. So if these spacecraft were designed to be serviceable and that could be updated and modified, then that could really help kind of diminish this amount of debris that we're just adding to that space.
Well, if we got each of the Starlink satellites to latch onto an existing satellite and fire a little retro rocket and bring, would that be okay? No.
I was just talking to my uncle last night, and he was saying, well, we could just paint all these satellites like that Vanta black.
Yeah.
Pigment, and then you wouldn't even see them in the sky. Problem solved. But I mean,
Vanta black is expensive. Holy smokes.
Yeah. There's another one that's cheaper apparently. I forget.
Yeah.
Also, would that not anyway?
Yeah,
we'll leave it to the satellite folks, but I feel like that would end up half the time absorbing a ton of heat,
radiation. Yeah.
Well, yeah. Anyway, we'll leave that to the satellite.
Yeah, these are very poignant questions from the chat. I'm
picking the best ones in all fairness.
I'm not the most qualified to answer these questions, but they are very prominent issues that are being discussed in the space sector. So if these are questions that you're interested in, follow up on them. There's so much room for this kind of insight and knowledge and excitement to make a splash in the industry. So
on that note about space pollution from defunct satellites and stuff like that, I do know, I have a friend who works in the satellite industry, and I know that now satellites have to deorbit after their mission is complete in a certain period of time, but that wasn't the case before when they were sending satellites up. And I also don't know how other countries do it. I don't know if it's just like a Canadian thing or if it's an international agreement. I don't know any of this stuff. I should go and check out the SGAC.
Whereas we do have a space policy project group.
There you go. Okay. Okay, so I'm going to jump into some of the Mars questions now. I'm afraid we're not going to be able to get to everybody's, but I'm going to ask the ones that will lead to the most discussion, and also the ones that I have a vested interest in. If anyone else has any vested
Joy
interest.
of being a leader.
So I was curious about this as well. This one's from Fraser. What specific instruments does Perseverance carry to look for life? And to attach onto that question, I wanted to just generally talk about like looking for life in chemicals versus looking for life in fossils. And then I'll ask a question after that.
Yeah, so Perseverance has several instruments. A lot of them are designed to, again, kind of get this context, so understand the habitability of the local region around the Mars rover, and that obviously contributes to this discussion of searching for life on Mars, because we want to look for fossils, or these chemical fossils, in the types of rocks that we think would have preserved those traces, or also would have corresponded to habitable settings. So that these kind of context instruments are totally relevant to that question. And so we can kind of break up Perseverance's instrument load into the remote sensing instruments and the contact science instruments. So these remote sensing ones, and these are the ones that I work specifically with. They're the ones that, again, they survey that area around the rover. They kind of try to map out all the targets in the area, and then we pick the most compelling ones and then drive the rover to those. And when we picked this maybe compelling, exciting candidate target that we think, okay, this is a good one to explore further, then we have the contact science. And the contact science instruments are the one that they're sitting on the, I don't know how well you can see me, on the arm of the rover. And that arm of the rover can be used to contact the rocks. That's why it's called contact science. And that arm, it has a drill. Yeah, that's a great picture of the rover. And so we can drill into the rock. And then one of the main instruments, there's the Sherlock and Watson instrument suite. I love the name. Don't ask me to tell you what that acronym means, because I do not know. But Sherlock, it's a Raman spectrometer. So this is looking for those organic traces of life. So a Raman spectrometer, it's sensitive to the molecular structure of molecules. Yep, Sherlock. So it's looking for the molecular structures that are consistent to these biological molecules, or these molecules that we know life produces during its biological processes. So Sherlock is specifically designed to look for the molecular signatures of those kind of biomolecules. And Watson is its co-operator, and it's a camera that's going to take these really high resolution pictures of the surface, right, where we take those Raman instruments. So we have context of what we're actually measuring, what kind of rocks we're looking at, what kind of textures are associated with those molecular signatures. So that's probably the key life detection instrument on the Perseverance rover. And then as well as the beyond just the rover aspect of the mission, Perseverance is part of kind of a longer term goal of drilling into the Martian surface, collecting these small drill core samples, caching them, and either creating a pile of these core samples on Earth, or kind of scattering them out like a trail of breadcrumbs behind the rover, which in the future, potentially 2030 kind of timeline, another rover called the Fetch rover will travel all the way to Mars. It's going to pick up those rock samples, take them up into orbit, and then another spacecraft is going to pick them up and fly them back to Earth, where then they will be decontaminated or kept in the sterile vaults and studied in these very clean labs on Earth. And that's going to be, and then we can subject these samples to as much scientific rigor and the most high resolution analyses that we have available to us on Earth. And I would imagine that some of those samples would also just be put away, locked away, with the very clear understanding that there is more to learn, there are more instruments to be built, and that we will get smarter with time. And so every few decades or so, we'll just go re-access those samples and subject them to the most recent and most modern and most high resolution analyses that we can. So that's probably, and there is discussion in the scientific community that probably we won't be able to make an unambiguous detection of life on Mars in situ, in contact, and that really answering that question and confirming a detection of life, if we think we have one, is going to come from these Earth-based analyses, because this is when we can get better resolution and subject it to more complementary lines of evidence.
So is it ever tantalizing, though, that these samples are just going to be sitting there for years, decades, until we get the funding to send?
I know, and that's the thing, is the Fetch rover. So this rover that's going to go pick up all those samples is not confirmed yet. It's not a done deal. So it was fun.
It's tease. It's just they're gonna sit
was a
there for
tease.
so long. This amazing science is just gonna sit there waiting for us.
But it is amazing science. So you can be a little patient for the big payoff that's going to come down the line.
And if we have any younger audience members, that's the generation that's going to be doing some of this cool stuff.
Yeah.
So just a heads
So
up.
get a foot in the door now and analyze return samples.
Yeah.
That's
That's actually
also secretly my motivation. It's like, okay, if I can start getting involved in the rover now, then maybe I'll be in line to start looking at these samples coming back.
Erin, would you go to Mars to collect samples yourself?
I would go to Mars if I could come back. I am not.
You're not a colonist.
No, I am not committed to this one-way
Tourist
trip
or
that
colonist.
people are talking about. I mean, half the fun is coming back and being able to tell people about it. Like I want to, and I don't
Do your analysis in the lab.
Yeah. So yeah, I would go to Mars if I could come back.
Perfect.
No one-way trip. And I like going outside. I like the trees. I got to come back.
The air's
I like
nice
it.
here.
Big fan of Earth. Big fan of Mars. Bigger fan of Earth.
sure like breathing.
Yeah.
Oxygen.
Breathing. Love going outside.
I have one last question, and then do each of you, if I know it's 9:10 and we're getting to Mars time, but if each of you have one more quick question, maybe we can ask them. My question was going to be following up on the looking for essentially biosignatures, and because of the recent news about Venus and this phosphine signature, which we in our context we only know to be created in a process that involves life, but that doesn't completely rule everything out. And so you mentioned that some of the stuff that you're looking for there, I guess, is there something that you could find that you would go, that has to be from life, or is there always going to be that question until you actually get the samples back?
Good question.
That's a good question. I think there are biosignatures that are definitely more rigorous, I guess. So if you found DNA, that would be a pretty great biosignature, kind of unarguable sign of life, especially if you're finding it alongside other lines of evidence for life and in an environment that we think would be habitable, and you find DNA, that would be really cool. Not my problem, but the issue with DNA is it's a very fragile molecule. So it's breaking down on pretty short timescales. It's definitely not surviving billions of years from the Noachian. So targeting those types of molecules, which maybe have more scientific or biological power for diagnosing something as a biosignature, don't have the stability to correspond to those ancient time periods that we maybe think the biosphere is most active. And so what I will be focusing on my research is these molecules called lipids. And lipids are fundamental components of cell membranes. So every cell, every living organism, every form of life as we know it, from the simplest bacteria to human beings, we all have cells. We all have cell membranes that are composed of lipids. And lipids are really cool because they're quite stable. They're called chemically recalcitrant. So they survive for geological timescales. So billions of years, they can be preserved in rocks and maintained. They're not perfectly maintained. They break down a little bit, but you can still recognize them as a lipid. And so those would be really cool signatures to find on Mars. If we found lipids on Mars, that would be really cool. Again, these lipids can break down into smaller molecules, and those are less diagnostic as life forms. And so if you find kind of these short chain carbons, that's maybe not as compelling as a biosignature, but it might be a piece of a lipid. So again, it's kind of building up. There's no one biosignature that's going to cinch the question, really, I don't think. It really has to be in the context of a habitable environment, alongside other complementary lines of evidence that are really kind of converging on this conclusion that this is a biosignature.
Okay, cool. Thank you very much. I know that folks get really excited about the whole, life on Venus, and almost every astronomer is really quick to be like, no.
Not necessarily.
And this is what I mean with complementary lines of evidence. You really need to believe it, especially if to make, extraordinary claims require extraordinary evidence, right? If we're going to look for life beyond Earth, we really if we're going to claim that, we have to be sure. And so there has to be several different reasons to believe that this thing is alive beyond Earth. And then that's when I would be convinced. But there has to be multiple points to hang your hat on.
That's very fair. John, Ryan, Chris, any last questions for Erin?
Yes, but I'll do a quick one because I just for the younger parts of our audience, those who are considering a career in space science or astronomy or geology or biology, Erin, what gave you kind of your spark and got you interested in science, astronomy, biology, geology, and anything that you remember from your early life that really kicked you into gear and got you to where you are now?
Yeah, well, I mean, I've always been into rocks. My mom was very much kind of the type that would pull over on the side of a road and we would look at these like road cuts that they blast them out for highways. So I've always been super jazzed about rocks. I honestly didn't know that you could have a career in rocks or in earth science and geology. I didn't know that that was a viable career option until I went to university. And I kind of knew I was interested in space. I mean, at some point I thought maybe I'd be a psychiatrist, but so I was kind of excited about the cosmos and space. But when I started university, my only impression of space science was astrophysics. So I started in physics. I started with the intention of going into astrophysics, and I realized I didn't really like it. It was like I like being able to hold things and like have it more tangible. So astrophysics was a bit like too removed for me to be really engaged with it. And then so this professor kind of off the cuff just mentioned, well, you know, why don't you do earth science and then use Earth as this kind of model to study other planets? Okay. It's just like this perfect, exactly, like just total like brain moment. And so it's this perfect merging of like, well, I love rocks. I love like kind of going outside and hiking. Being a geologist is basically just like glorified hiking and like collecting rocks. So I love it. So I get to do that and then study other planets at the same time. And yeah, so and this is what I meant. There's so much multidisciplinarity in space science. Like you can kind of start wherever you want to start. That field is pretty much going to contribute to space exploration or just moving humanity like one step further in scientific understanding, which is fundamentally contributing to space science. So that was a long-winded answer of just
no, we got it. Geology,
good answer.
We got it.
Yeah.
But
yeah.
Yeah, it's very serendipitous in university. Just kind of explore things that you're interested in. You'll fall into something that you love.
Yeah, don't burn any bridges. Don't cut off your options.
No, and just talk to people. Tell people what you're interested and excited about. Again, I had no idea that earth science was a career until, you know, people knew that I was kind of interested in that. They're like, well, why don't you be a geologist? I was like, oh, okay. So just, yeah, tell people what you're interested in. Or if you find somebody who has kind of the career you want, or they're doing something you think is interesting, or like you meet the person who kind of embodies all of your career goals, just like talk to them. Like, what did you do? How did you get here? What is your advice? Just talk to people.
So similar question, where do you want to be 10 years from now?
Ooh, on Mars, as long as I can come back. But no, like where I would like to land in my career is I want to be involved in space missions. So this is why I'm so stoked to be involved in the Perseverance rover mission now in graduate school. Like this is way earlier than I ever expected to start being involved in space missions. So I'm just like thanking all of my lucky stars that I get to do this as like an actual like real thing right now. But I want to be part of the effort that gets humans to Mars. If I can go, that is great. If I can just help enable other human beings to explore Mars, whether it's in my lifetime or after it, that's fine. I just want to be part of that cohort that enables that type of exploration to be done. Boots on the ground on Mars.
Fantastic.
You need to be ensconced safely in your Phobos base, telerobotically operating your avatar, your geological avatar down on the surface.
That would be just fine.
That's going to be the Perseverance rover, though, because you were telling us before we started, you did some training to operate the rover, correct?
Yeah. So Perseverance is about 30% of its way to Mars. It's about a third of its way on its journey. And so I've just started my training of how to drive the rover once we land on the surface. The first couple days and weeks, it's a lot of testing, making sure like all the arm movements work, the wheels are turning, the rover is healthy, everything is green. And then after that, the rover is going to start roving and driving and looking at rocks and doing experiments. And so I'm going to be part of the team that's driving the rover and picking which rocks we explore and which rocks we shoot lasers at and what it means when we shoot the lasers at the rocks. And so I had my first training session last Monday and Tuesday. It was called an operational readiness test. So we're testing the software, seeing if the scientists know how to use the software, which I didn't, but now I'm learning. We have another test in November. So over time, yeah, we're just going to build up this expertise of how to drive this rover. Yeah, and I'm just jazzed.
I'm
It was
so excited for you.
I was telling these guys on the call, during our operational readiness test, we were simulating rover operations, and we were looking at a test bed, which was in JPL, so in California. We were just looking at sand and some laboratory floor, but it was so exciting, and I was so jazzed. My head was so into it, and I was so like not convinced in my mind, but imagining that this place was Mars. And I'm just so excited for these rock samples to actually be Martian rocks, and I'm so ready to just not be in a California test bed and to be on another planet.
It's so exciting. That's awesome. Oh man. Chris, any last questions?
No, I think we've talked, we've run her through the mill. I'm good.
Yeah. Sorry,
It's been fantastic though. We could go all night.
No, it's fine.
Thank
I just had my PhD qualifying exams, and this was, it was 3 hours of grilling me about what I'm going to study for the next 3 years. So this is perfect.
Well, congrats on finishing that. That's a tough step.
Yeah, terrific.
For sure. That's amazing. We have a request from Marijana that if maybe next year you can spare some time to talk about your driving experience with the rover. That'd be kind of cool.
Yeah, you don't have to ask me. You don't have to convince me too hard to talk about Mars with you. So
Great.
Thank you so much for sharing your time with us today. I've learned a ton. I think we've all learned a ton. We've had a great time chatting with you. We really appreciate the time that you shared with us. And yeah, just huge thank you.
Thank you guys. And thank you everybody for being so active in the chat. It's really nice when people engage with these types of events. So thank you all for coming out and for giving me an hour of your time to talk about Mars. I really appreciate it.
You're welcome to stay as long as you'd like if you'd like to look at Mars tonight. But you're also welcome to, if it's, the evening and you're not a functional insomniac, you're welcome to also leave. Whatever you'd like. Okay, okay, sounds good. So we're now going to move on to our observing time. The rain has stopped here, but that doesn't mean that we can see Mars here, unfortunately. Chris, do you know how things are looking in Toronto?
I haven't been outside to look, but
okay.
Yeah.
So we'll get
my friend Eric Briggs was planning to do some live streaming from Buffalo. I know he's watching. I'm not sure if he can report to us how he's doing.
He did. He said that Mars was going to peek over the top of the trees at about 9 p.m. So we're after 9 p.m. Eric is one of our RASC board members as well. So he may be able to provide us with a live view, and we can promote him to a panelist if he does get a view. And until we hear from Eric, Chris, can you tell us a little bit just in general about opposition, closest approach, and all the stuff that's going on this past week?
Let's just set the stage and talk about why we're here, what this is all about. So I'll just show a couple of things here. Let me show my screen one. Share. So what I'm showing here is a schematic diagram of the solar system looking down from above. And from our vantage point on Earth, we've got two neighbors that are closer to the sun than us, the inner planets, Mercury and Venus. And then the rest of the planets are farther from us from the sun, including Mars and out from there. And so we call the Mercury and Venus the inner planets, and the Mars and Jupiter, Saturn, etc., the outer planets. And so if a planet is closer to the sun than us, then it never ventures that far from the sun from our point of view. So we'll get Mercury and Venus visible, in the pre-dawn or the post-sunset sky, but they kind of stick to within an hour or two or a few hours of the sun, either rising before it or setting after it. And the things that it can do, the inner planets can do, they can line up with the sun and disappear from our vantage point because of the sun's glare. That's called conjunction. And a conjunction can occur when the planet is between us and the sun, or when it's on the far side of the solar system, from far side of the sun from us. These are both conjunctions. One's an inferior, one's a superior. And then the times when they're most visible is when they sort of reach the outer turn of their orbits. And we call these elongations. So if they're up in the evening sky, we call them eastern elongations. And if they're in the morning sky, we call them western elongations. But what we're here for this week is an opposition. So an opposition is what happens when the Earth ends up between the sun and the planet. And so when that happens, we're on the same side of the solar system as that planet, and we tend to be at our minimum distance from it. And that means that the planet will look larger and brighter in the sky for a number of days or weeks. And also it'll because it's opposite the sun, it'll rise when the sun goes down and then set as the sun comes up. So we get all night views of it. I'm going to switch over to my program here. Let's see if I can get rid of this diagram for a second here. So I'm going to show you a top-down view of the solar system. Kind of the same idea. There we go. Open this one up. This is a schematic diagram of what's going on. So the Earth's orbit in green and Mars's orbit's in red. And this is not really to scale. I've enlarged the two planets so that you can see them more clearly. Mars is about half the size of Earth. And Mars's orbit is about 40%, 50% larger or farther from the sun than the Earth's is. And so that means that when the Earth completes an orbit around the sun once in a year, Mars isn't finished orbiting the sun. We're much faster. So in a year from now, this is the date tonight. If I jump ahead a year, Earth will go all the way around the sun and come back to where it was. And you can see that Mars will land on the opposite side of the solar system from us in a year. And then in 2 years, we're back in the same area, but it takes a couple more months for us to be in opposition again. It's about every 2 years and 50 days that the two planets line up. So I'm going to go back to now. You can also see that the sun is sort of nicely centered in Earth's orbit, but it's a little offset from Mars's orbit. So Mars has we call it an elliptical orbit, and it's not as symmetrical. And so Mars varies in its distance from the sun by about 20%. Where Earth is much, much less. It's only a few percent difference. And so at those times when we hit opposition, depending on what sort of spots they arrive at, or sort of they meet up, you can have situations where the two planets are very close together, or times when they're very far apart. And so you can see that this current opposition is one where it's not the closest, but it's a relatively nice close meetup. And you can also notice that the orbits are widening. So the planets are going counterclockwise in this view. So that the orbits are diverging a little bit at this time of the year. And that means that about a week ago is when Mars was absolutely closest to Earth for this meeting. But it's now a week later that we have the lineup at opposition. I've got one other cool picture here I'll just bring up to finish up. So this is the same picture, but now what I've done is I've added all the times when Earth and Mars will be at opposition heading into the future, and then a couple in the past as well. So this radial line connects Earth and Mars on October 13th, 2020. The next time they're going to meet up is in 2 years and 50 days. That's December 8th, 2022. And I think Ryan or John is going to talk about the significance of the time of year when the planets meet up. But the next really close approach, if we sort of march ahead in 2 year, 50-day intervals here, we come around, September 15th, 2035 is the next time we'll be this close to Mars. And so that's why Mars looks bigger and brighter in the telescope, nice big fat disk. The one that you're gonna be watching out for, especially the younger group watching, is August 14th, 2050. That's gonna be one of the absolute closest next opposition events. At that time, we're only going to be 56 million kilometers from Mars. And that would be equivalent to about 3 minutes radio travel time between the two planets, as opposed to February 19, 2027, where we're going to be 101 million kilometers apart. So it's a much less favorable opposition. So that sort of sets the stage for everybody, and I'll pass it on to one of the other gentlemen to continue on.
So it sounds like Eric may have some line of sight issues with Mars right now, that there may be some leaves in the way. Eric, are you able to stream right now? I don't know if you can, if you're listening at the moment.
Hi, Jenna, I didn't quite catch your question. Were you asking me to stick around, or?
Are you able to stream right now? Are the leaves out of the way, or should we wait a few extra minutes?
Actually, the monitor that I'm using to stream has gone out, and I'm not quite sure what that means, if it's become disconnected or whatever. Give me a second, please. Sorry.
Okie dokie. then I'm going to send over to Ryan just to briefly talk about when the best time to view planets is. And I'm going to also share my screen with some video of planets that we have seen over the summer. So Ryan, over to you. If you want to visualize, please visualize away.
That's what I do. Yeah, definitely. You know, Mars is rising just at sunset this evening. So I'm just bringing up Stellarium here. And we can see that right now, the time is right now. Mars is quite a bit higher. Now, this is also from my point of view, just north of Toronto. So for me at sunset, Mars rose, and it's getting up high above. We'll just go back in time just a little bit. You can see we also have Uranus in the sky. But just there, you can see it's as the sun sets, Mars rises up. And of course, the best time to see a planet isn't when it first rises, because Earth has atmosphere. Atmosphere not blocks, but causes that rippling effect, right? Moving air causes the planets to ripple, causes the stars to twinkle. And it gets a little bit better especially if you're doing imaging or trying to take a good, clear view of a big, beautiful planet at opposition as the planet gets a little bit higher up in the sky. And so as the night goes on, Mars gets a little bit higher. Gosh, I wish the weather was as good as it is in Stellarium. Always really nice in there. And then if we move over toward the south and southwest, you can see Saturn and Jupiter slowly closing in on each other. They're also really good targets to look at right now, tonight. But for any of those younger viewers, those people who are just going outside to use their eyes, the best instrument that they have, to go and look at planets for the first time, the little secret is look for the ones that aren't really twinkling that much, because planets don't twinkle like stars do. Right? So and especially if Mars is nice and bright and red. So if you do go outside tonight, tomorrow, a week from now, go out, use your eyes or pair of binoculars or whatever you can get your hands on to just go out and take a look at these planets. Mars being at opposition is big and beautiful and bright. Jupiter and Saturn are not far from one another. Just go out and use your eyes and be the astronomer that we know you all are. So that may be nothing like what Jenna wanted me to talk about, but that was, I thought that was a nice one.
It was very nice. It was very heartwarming. It wasn't what I was expecting, but it was lovely.
Ryan, can you tell us the best time of the night to see the planet right now these days?
I'm going to show a video of Saturn while you do.
Best time of the night to see the planet?
Well, when is it nice and high and out of the Earth's interfering atmosphere that much?
Well,
is there an optimal time?
11:15 right now, and it's pretty high up. Like if we look at the altitude's about 44 degrees now at 11:30. So it's reaching its highest point around midnight, maybe a little bit after.
So basically, when it's high up in the sky, there's less atmosphere that you're looking through. So the higher up it is, the better it looks. This video that I'm showing you right now with Saturn was taken, I think in June or July, what even is time in quarantine. It was sometime taken in the middle of summer, which meant that that's when opposition is for both Jupiter and Saturn, but they're really low on the horizon because the sun on the opposite side of the sky is really high. And so you can see that like shimmering, and also there's a little bit of jiggling from me shaking the telescope there, for example. And the shimmering is why you want to have Mars high up in the sky. And it's why this opposition is a good one, because Mars is relatively high in the sky right now. And the next opposition in December will be really good too, because in the winter, the nighttime objects that are on the same plane as the sun, so like the moon, the planets, they're really high in the sky, whereas in the summer the sun's really high in the sky and the nighttime objects are really low. So middle of winter is a really good time if you're not prone to being chilly.
So that's another reason why this opposition is so great for everybody, because Mars is nice and high, not super high, but way better than last time. So in 2018, it was a July opposition, and Mars only reached a maximum of about 21 degrees above the horizon. So it was stuck in that murk, that's distorting atmosphere. This time we've got 50 degrees maximum height, which is fantastic. So, and by the way, for those that can afford it, whenever a planet's at opposition, you can always travel south, and the planets get nice and high if you go further south. So if you're really keen to
Look at
see
that.
Mars at opposition, even in the summer, just get down near the equator and Mars is right over your head almost. So
And then climb a mountain and it gets even clearer.
yeah,
Yeah, totally.
Kind of nice we don't have a moon as well, right? I mean, the moon's
Yeah.
just about new. So, I mean, that's usually more important if you're looking at a meteor shower or something, but just not having the moon there is that extra light that you don't have. You get a bit more contrast with the planet.
I dragged a bunch of my friends out the other night to go look at Mars, and I also forced them to wait for the moon to come up so that I could show them the moon as well. I felt very bad. We stayed up until like 11:15, 11:30. Just, I know it's cold, everybody, but I promise it'll be worth it. All right, Eric, I see slight movement. How are you doing with telescopes and monitors and stuff? Uh-oh.
so
He
if
does
you
have
want,
aliens in his profile picture.
I could
yes.
play us a pre-recorded video, some live Mars that we saw at the David Dunlop Observatory a couple of nights ago, just
Yes,
to whet
please.
people's appetite. So let's see if I can do that for you here.
So for those who do not know what the David Dunlop Observatory is, it is an observatory in Richmond Hill, built in 1932, completed in 1932, and it's Canada's second largest optical telescope, I think.
Yes. So I'm gonna show you, before I do the DDO one, I'll do one from my friend Rick Foster, who lives in Markham, and he is a great planetary imager. So let's look at his little video. It's just about 2 minutes long.
Hello everyone, it's Rick Foster here, and it's my pleasure to present here a live recording of Mars taken very recently, October 9th at 1 a.m. From my home in Markham. I normally do the shooting like this from my front driveway, and it's fun actually. As the neighbors walk by, they'll sometimes come over and have a look-see what's on the laptop or view through the eyepiece. It's always a lot of fun. The neighbors know me as the crazy astronomer. This was taken with my Celestron Edge HD 11-inch in Alt-Az configuration. The camera used today is an ASI 120 MCS. I wanted to have a color view to present to everyone. Magnification is pretty high. It's a 4x Teleview Barlow, but I find that being so bright, that high magnification can still allow the image to show up fine on a sensor. To sharpen the view a little bit, I'm using something called an atmospheric dispersion corrector that corrects for atmospheric dispersion. This is where the different colors in the spectrum will diffract at different angles. So the red will be less affected by the air than the green and the blue. So the dispersion corrector kind of realigns all the colors here. You can see there's almost no color fringing top and bottom. The blue in the top, red in the bottom, but you know, maybe I could do better next time. So yeah, some of the features we're looking at, obviously the bright southern polar ice cap. The upper left would be the Syrtis Major. This is the very pronounced dark area upper left. And yeah, to the left of it would be Libya, and to the right would be Area, and below it, towards the polar ice cap, would be that bright region Hellas. So the atmosphere is allowing a lot of these features through, so it's nice to see that. And yeah, enjoy the view, guys, and clear skies. Over to you, Denise.
All right, so just by way of a bit of explanation, what I can do is I can show you what Rick was showing us through his telescope. So you may have noticed that there was a dark wedge shaped area that was sticking up across the girdle of the planet. That's the Syrtis Major area he was talking about. So we have the dark areas on Mars are these basaltic exposed rock, the dark, heavy basaltic rock. The lighter areas tend to be the areas that have been covered by dust and sand and various wind-blown sediments and things like that. So when you're looking through your telescope at Mars, you want to look for you can look for these light and dark patterns. You won't perhaps get as good a look as Rick did. He's a real pro at it, but really any size telescope should do the job. And the bright oval here near the bottom that I'm circling right now, that's the big Hellas impact basin that I asked the question about a little bit earlier. So if you like, I could show another video, or we could go on to something else. Jenna, what do you think?
I think let's save your last video, because you mentioned, or not you mentioned, in the video that Rick sent you, he showed you, first of all, he showed us the video as it looks if you were looking through the eyepiece essentially. And then he showed the final processed image, which was like wildly different. And so I'm going to throw this to John, who has like 1,000 telescopes behind him and several different imaging setups, who seems like he knows things based solely on that, but also the fact that he's written books on these sorts of things. So John, can you tell us about Lucky Imaging, please?
Sure, Jenna. Well, I'd like to go back and just say that, I just love looking at Mars visually, and that's sort of my background as a visual astronomer. And so this astrophotography thing is fairly new to me, although I love, the past, 5 or 6 years, I love just using the phone to get pictures. But it's only been since COVID that I've actually picked up designated astronomy cameras, and I'm trying to like claw my way at high speed into this hobby of astrophotography, which is very different from just sort of casual stargazing. So what I wanted to do, and you guys totally interrupt me as often as you can and bombard me with questions that I probably won't have the answers to, but it'll be great fun, is to sort of divide planetary astrophotography into sort of 3 groups. One for the beginner, and then the intermediate, where pretty much I am, and then the advanced, where, some of you guys might be.
Where Rick was.
Where Rick was, exactly. So if you've got a basic telescope, let's say like this $200 one that I just got from Costco last week, it has, with a 20 millimeter eyepiece, it gives 30 magnification. Well, I looked at Mars, 2 nights ago. I was actually in the middle of nowhere in Nova Scotia. We had Bortle 1 skies, and I actually had a great view of Mars just through this $200 telescope that I was testing for someone. And so what you're tempted to do is then go and put your cell phone on, just literally holding it up. And so it is possible to get okay images of Mars, and you might even be able to detect the ice cap in your iPhone picture, and you might be able to detect some of that the discoloration in the Martian soil. But it's very difficult to do that just by taking a picture. You'll probably just get that, white smudge. And so there's a couple things you could do just with software to be able to do that. And so if you're just a beginner and all you have is the phone and a little telescope, one piece of software, if it's an iPhone, you can use an app called Nightcap. Maybe I can bring it up here, but it's an app. I think it's $2 or $3. But what it enables you to do is, okay, my phone's not turning on here, is to just have total control over the focus and exposure and ISO on the phone. And so by doing that, you can tone the brightness way down because the phone is looking at dark. And so it wants to make everything bright. So initially your phone is going to overexpose the planet, but you can use, if you don't have Nightcap, just use the slider and pull that brightness down as far as you can. Or if you do have the app, then adjust your ISO and focus so you can actually see the planet as clear as you can. And the second thing you need to do after, so what you're going to do is just record a video. Should clarify, you're not taking a picture, you're going to get a video of the planet because that comes in later. You're going to export that video. If I'm just using the phone, I'm just going to take, maybe 10 seconds at most, and then I'm going to crop it to the edges to avoid the shaking from sort of hitting, the shutter. Then what are you going to do after you've probably got this image of Mars bouncing all over the place because you're just holding the phone, and you're going to use software called PIPP. And I sent Jenna a bunch of links that she can drop in to the chat there. And what that's going to do, PIPP is going to take that bouncing around image of Mars and it's going to stick it in the center of a video, and it's going to export an AVI file. And now you have a picture of Mars that's centered, and you're going to have all your frames. So if it's 10 seconds, that might be, 500 frames. And then what you're going to do is get software called Registax. And there's all sorts of tutorials on how to use it. But essentially, you're going to hit a button that says Align. So you're going to open that file, the AVI file from PIPP in Registax, hit Align. And then limit, and then stack. And that is going to take those 1,000 frames and turn them into one image. And again, we could show you a whole demo of that, but that would take probably more time than we have.
So I'm actually, and I know that you have like 8 other levels of astrophotography for you to go through, but I'm going to stop you early because Eric has a view. Is it okay if I just quickly show an unprocessed video and the final processed image of Mars?
Absolutely.
Okay, cool. So this shout out to Killarney Provincial Park, which has an observatory. For those of you who do not know, it has 2 telescopes that you can rent. Actually, you don't rent. You put a deposit down of $250, I believe, for the night, which you get back in the morning if you don't destroy them. Hopefully you don't. And there's a 10-inch and a 16-inch. This is from the 16-inch telescope there, taken by the observatory staff. So this is the unprocessed video, and bearing in mind that the seeing when this was taken, which would have been end of September, was terrible. And the seeing, what I mean by the seeing is that like shimmering of the atmosphere. So the seeing was just awful, which is a shame because it's such a great telescope. And you can see it kind of like picking up some details sometimes, and then it kind of fades away. And then it picks up details again, and then it fades away as the atmosphere clears up. And so maybe John, can you talk about that lucky imaging process? And I'll bring up after I let this run for a little bit, I'll bring up the final processed photo.
Yeah, so the lucky imaging, as I said, maybe if you're taking 1,000 or even 5,000 frames, when you go to stack the images, you're going to tell the computer to take the best X percentage. So I did one and I actually had really poor seeing, so I'm telling the computer only take 15% of my images. So if you're taking 1,000,
right?
Pardon?
The top 15, yeah.
Yeah, the top 15% of those frames. So the best 15. So best 150 of that 1,000. And so, and then what the computer is going to do is it's only going to stack the best images together. And I think some of the software even takes the best pieces of the best images. So there's definitely different levels of stacking software as well. So that's what lucky imaging is. So the computer is analyzing the images. You know that some of the frames are going to be clearer than others. And so those are the ones that the computer keeps.
And keeps and stacks together to make the best image.
Yep.
This is really only a planetary technique. So just a heads up if this is like something that only really works with the planets or the moon, for example. So having seen this video for several minutes now, you can see that it's pretty darn blurry, but every once in a while, the images come into like sharp focus. And so I'm going to bring up the final image, which was also the promo image for this talk. So this was the final image that the staff created from that video. So you get pretty good detail considering that was just a big blurry mess, or at least it seemed to be a big blurry mess. So the technique really works well for picking up details on these planets. And if you are particularly interested, the fellow who put this together for us, who tends not to like to be named, even though he's fantastic, even labeled all of the different parts of it for us too, that you can see with the southern polar cap and Olympus Mons.
Very good.
Yeah. So
it's summer it's summer at the South Pole on Mars right now. I don't know if anybody mentioned that yet. So the polar cap, although it's a little bright spot, it's actually shrinking. So you may not see it as well as you'd like, or as you expect if you've got your own telescope.
Yes, and this, in all fairness, this image was also taken 2 weeks ago too. So I don't know if that makes much of a difference.
And someone in the comments just asked how the computer selects, and I'm not 100% sure, but it might be just looking at a graph and of the focus of the image and doing the half max or a full width half max calculation.
Yeah, it analyzes the sharpness of each frame. And
so this
and that's free. Is Registax free?
Yeah, PIP is free, Registax is free, and if you want to, Nightcap is $5 or something.
I used AutoStackert, and we have a video in a previous Insider's Guide to the Galaxy episode on our YouTube channel about how to do this process. So if you're interested, subscribe, and you can go back and find it in the.
If you have time to show Claudio's video in a little bit, I can show you. He's gone through the process and he has some amazing results. If we get a chance.
Cool.
Yeah,
I'm gonna give Eric Briggs a chance because apparently, he's already on it. He's got the live view ready to go. Amazing.
Hey.
All right.
Sweet. So that's what you're seeing right now, Eric? He's mute. FYI, you're just muted. I'm not sure if you know. Or he doesn't want to talk. Either one.
Mute. There we go.
There you are.
There he is.
What I was seeing just a few seconds ago. Whoops. we go. You'll probably see a little bit of a jump in 30 seconds, but it will come back.
Okay.
I'd like to tell you a little bit about what I'm using right here. This is a Raspberry Pi 4, which is a small credit card sized computer, which costs about $60. And I've attached a Raspberry Pi HQ camera to it. That costs about $70. And I'm operating it from the command line with a software called Docker. I don't have all that much control over what I get, but Docker allows me to stream directly to YouTube. So I wonder if I can make my my timeline go away there. That'd be better. So I'm actually showing you what I'm seeing on YouTube after bouncing it from the Raspberry Pi to my laptop.
Wow.
Works okay.
That's super cool.
Mm-hmm.
You can see the dark regions across the belly and across the equator.
Let me know if you think that this image is too bright.
It's actually, so it's toned down since you started and it's kind of coming in and out of brightness a little bit, but it looks pretty good. We can see the dark feature in the middle.
Yeah, the sky is mostly clear. It's just gone past a few small clouds, but it's mostly clear. And I have a couple of masking solutions for making the image a little bit dimmer if we want. So I'm just going to put my focus mask in place. Focus mask is a really useful thing to have when you're taking planet photos.
We really see that rippling from the atmosphere.
Yeah.
So this is blocking it down from about an 8-inch aperture to about 21 square inches. That's about as good as I can get on focus. You'll probably see it go dimmer now. Let me know if that's too dim.
That's a bit too dim, I think. But it's
too dim. Okay.
We're getting a bit more detail, I think, though, aren't we?
Get more feature.
And I've also made a different mask that takes it down to about 28 square inches.
Okay.
So for folks that have telescopes at home and that want to look at Mars, tonight is not the only night you can look, right? Mars will be great for the next few weeks. So take every opportunity that's clear and grab your look. The other thing is you want to look for a good long time so that you're waiting for the air to stabilize and you get those crisp views.
Mm-hmm.
And yeah, if it's too bright, some telescopes have a small cap that you use for the moon. You can put that in place to dim down Mars, or you could put on your moon filter and dim down Mars and use that.
And now, Eric, are you using an 8-inch telescope?
Has he disappeared? I think he is. I think that's what he said, eh?
Yeah, so it's probably, I'm assuming it's identical to this one, pretty much. So
Identical to which, sorry? Was that right?
Are you using a C8 or a C8 Edge?
C8.
A C8, yeah. So he's basically using this one. And then what types of masks did you put on?
I'm using a C8 with 2x Barlow lens, and I have a Kendrick quick focus for focusing.
So there's a 2x Barlow right there.
That gives me 3 1.25 or 1.5 apertures. And
Okay.
I've made myself another temporary mask that's 1 3-inch aperture.
And so by masks,
One
you're
would
putting
be
that
pretty good
over
because
the,
it's not going to be obstructed by the central obstruction of the telescope.
so he's actually putting things like, here's a Badenoch mask.
Yeah.
You're fitting it over the primary, sort of like this. I don't know if you can see me.
I think whenever you're talking, they can see you. So go for it.
Yeah. So that I'm just trying to understand what he's doing. So, and because I want to do this too. I want to get better. And so I'm guessing he's almost got a mask like this, but cut a hole in it to make it smaller, and that's getting rid of some of the ripple.
Yeah. It's just a piece of card that I've cut a 3-inch hole in.
Okay.
So just offset from the center.
Yeah.
And what was the
I've
camera
done
again?
some streaming going back to 2018 using setups like this. Well, not streaming though. This is the first year that I've done streaming live to YouTube. When I started using the Raspberry Pi to take Mars images during its opposition in 2018, I was keeping all of the data on board the Pi. And I think the logic of it is pretty simple. when you take the images yourself and you keep all of the data on your own computer, you get the highest resolution.
Yeah.
If you stream it all to YouTube, you only get to keep what YouTube keeps. So this is okay, nevertheless.
Yeah, I found one of the challenges I have when I take the data, if I'm using a phone and I email it to myself, it compresses it, and then I get to my computer and I'm not dealing with the same data. And so that's been an issue that I struggle with in the beginning.
So I have a question, or there's a question from Pearl Van Geest here, which is how come Mars doesn't look as red as it does with the naked eye? So I guess what Pearl is referring to is when you look at it without without any telescopes or anything like that, it really does look like orange. And how come it looks a little bit more muted here?
I think that's probably due to, well, when something is brighter, you can actually perceive the colors in it more vividly. But it's the only thing that's in the image here. And I've seen some interesting side effects depending on what part of the chip that I'm on, and also how I set up the utility. When I do it this way, I don't really have much control over the image. But when I'm using the onboard RaspiVid utility from the Raspberry Pi, you got to code everything on the command line, which is a little bit irritating, but it allows you to pick ISO, pick dynamic range, pick exposure, things like that. In my experience, it's probably best to keep the coding simple. I've taken some pains to get the right image, but then I find that I end up with a less colorful image.
There's a lot of factors for colors, right? Everything from the observing conditions to the telescope to the camera to so many different things.
Yeah, I'd guess in this case it's just because it's so bright. Like when it went dim, there it was much redder.
And don't forget that, if you're not seeing Mars very clearly one night, don't give up. Try another night. It might just be the atmosphere was bad the night you tried.
Might get a little lucky.
Yeah. And so what are you using to keep it centered? Are you tracking? Are you guiding? What are you doing there?
Sorry, I was just putting my off-axis mask back in place for a second with tape so that I can sit down and have a good look at it.
Oh, there it is.
It's still looking dim on the live stream.
It just got a little dimmer. It was really bright a second ago.
Yeah, I think it looks too dim right now. I'm going
You need to be somewhere in between the two, and I think you'll be perfect. But we're seeing lots of detail in the dim image. That's great.
Yeah, you get to see some really good dark spots.
I'm so happy we can actually see it. I'm blown away by this view. This is incredible.
Yeah, and Eric, what was the camera again?
It's a Raspberry Pi HQ camera.
Okay, I've never heard of that.
And there's a couple of different cameras that come with the Raspberry Pi that are in the area of being like webcams. Back in 2003, when we were taking images of Mars, we were taking it with off-the-shelf USB webcams because that's what was cheap at the time. And you pulled the lens off of one of them and put and one of those old 1.25" diameter film can things, and it would fit into the telescope eyepiece holder. And there you would go. But 15 years later, people rarely use peripheral USB webcams. They're usually right in the middle of your laptop. So I didn't have one in 2018, but I did have a Raspberry Pi lying around, and I thought, well, here we go. This is the spirit of prototyping.
Very, very cool. We are swiftly approaching 10 p.m., which I had initially said was our time limit. But I figured now might be a good time, if you don't mind continuing to stream for us, Eric, and for which we're very grateful. Maybe answering some of the questions that were in the Q&A that we couldn't get to when Erin was here, that some other folks of ours might be able to answer. The first of which I figured at least someone could comment on how come Mars's magnetic field, or how come Mars didn't have a magnetic field, or how come it went away very quickly? And And then a question from Marijana to Chris: if the core was able to keep moving and magnetic field was maintained, hint to what the answer to that first question was, would there maybe be a higher chance of further life evolving on Mars?
Yeah, I think the answer to that would be yes.
Yeah.
You know, there's protection, right? Mars is smaller than Earth. It's core cooled more quickly, so you're going to lose the magnetic field. Although there have been discoveries of kind of intermittent magnetic fields rising up on Mars. So
Mars also has a lot of local magnetism in it. So if you look at a magnetic field map of Mars, you sort of zoom in, you'll see these little ones all over the planet. And I think that's just how, as the planet cooled, you know, the places under the surface that had, you know, nickel and iron just froze in those different, or, you know, solidified in these different positions, leaving their sort of magnetic fields behind. But I mean, they don't provide much protection from solar winds. So one thing that I thought was really cool is if in the far future, humans were to put the atmosphere back on Mars, you know, some people say, well, it would just blow away from the solar wind because there's no magnetic field. And that's true, but it would still take 5 million years or so. So if you were to actually put it back, you'd still be good for a couple million years of having that thick atmosphere, which I think is pretty cool.
I hadn't thought of it that way. I guess it would, yeah. That's pretty cool. And for clarity, because I asked a question that then was immediately answered in the form of another question, the reason that Mars doesn't have a magnetic field is because the core cooled and stopped moving. Our core on Earth is still warm and moving, and therefore can produce the magnetic field. But Mars is chilly. There was another question that I knew we could answer. Where did it go? How do you know if a meteorite came from Mars, and how does it get to Earth?
Oh, geez, well, sorry, I just keep jumping in with answers, but I'll give a little bit of it since I asked the question of our guest. But in a fairly chaotic early solar system, there's a lot of impacts. There's a lot of leftover rocks from the formation of the solar system, especially 3.84 billion years ago, in the late heavy bombardment era. And so there's lots of stuff smashing into planets, smashing into the moon, the Earth, lots of stuff going around. And so material can get kicked up from Mars into space and fly around the solar system for a few 100 million years. And then one of those rocks happens to fall on Earth as a meteorite. And that, I mean, those big collisions can happen later in Mars's history as well. And that's why I was kind of curious to ask about, well, did any of those happen in that very, what was the period she named? I had it here too.
It's the
Noachian period.
Yeah, Noachian.
Because that would be really interesting if we get that meteorite coming from Mars, being kicked up by an impact, falling on Earth, and then we find those elements that are those tracer molecules of life, those bits of evidence that give us some clues that there might have been life there. So that's why I was kind of curious about that. So that's how they tend to happen. And how we actually prove they're from Mars is that within the meteorite itself, there's little pockets of atmosphere trapped in that rock, in that impact. And you can compare that to the Martian atmosphere now, although it is pretty old. These rocks are pretty old. And then the composition of rocks as well. Chris, you probably know a bit more about this than me as a geologist, so please.
Yeah, so all the minerals that go into that collect together to make the minerals and the rocks that are produced from the minerals, they come in slightly different flavors. You may have heard of carbon-14, which is a different flavor of carbon, which is normally 12. So those are called isotopes, and so you get a sort of a chemical fingerprint made out of the rocks of a particular world. So Earth has a sort of particular fingerprint in its rocks. And Mars would be slightly different. So when we compare the ratio of the various isotopes of the chemicals that make the minerals, like the same mineral, you can find the same mineral from Mars and the same mineral from Earth, but the chemical abundance of those isotopes varies a little bit. You could say, well, this one is obviously not from here. It's different from a different planet. So all of those pieces of evidence, as Ryan said, fit together to prove that it's an alien meteorite.
And the Martian meteorites are rare, but they're not super rare. It's like 0.01% of all the meteorites we find in the Antarctic are supposed to be from Mars. So,
and of course, our rovers have seen lots of meteorites on Mars, but we don't know whether any of them might have come from Earth.
Ooh, this is where I think, Chris, you had mentioned that how much more information we could get if we just had people on Mars instead of the rovers looking. Like, it'd be so much faster.
Oh, they say that if you put a geologist down on Mars, she could do the same work in a few days that Curiosity's done in 8 years.
See, this is important. This is why it's important to send rovers, is so that they can do all the things that human beings would be wasting their time on. So that when we get to the limits of what our technology can do, the limits of what we can learn from having rovers there, we either build a lot of rovers or we send humans to do a whole bunch of scientific data collection, really valuable data collection in a really short time span. So the rovers are absolutely essential right now, and they're going to pave the way for deciding what the best science to do is when we send people to Mars.
Mm-hmm. Yeah, it would be a real shame if we sent a bunch of people to Mars and knew nothing about it to start with and brought all the wrong tools and had no idea where we were going with it any of it. So they certainly paved the way that way for sure. And
we have the technological spin-offs like the drone that's going to be attached to the belly of the Perseverance rover. That'll be the first time humans have flown an aircraft on another planet. And ingenuity. So we're learning every time we do it. There's so much exciting stuff going on when it comes to space exploration. And I wanted to mention this when Erin was around as well, that a lot of this is extremely intersectional. Like, you don't have to study astrophysics to do this. And she said that you can study biology and then do space stuff. You can take almost any job occupation title and add the word space in front of it, and it's going to exist someday. And my brother is thrilled about this because he's a wastewater engineer and he's always wanted to be a space plumber. Yeah. And that's someone's gonna need that someday. NASA actually just developed a new toilet as well. So technically, there are already space plumbers. How are we going to be able to make concrete when we get to Mars? Can we use the soil materials to make the things that we're used to using for building structures and things like that? All of the engineering know-how is going to need to be worked out.
And Mars farmers, there's a massive need. And I know there's actually quite a few researchers today working on Martian farming. There's a big trailer in Antarctica where they're growing things in hydroponics, getting ready for Mars.
That's actually really difficult to do because you need a good analogy of the Martian soil, right? We haven't collected Martian soil, so we have to kind of guess at what it's like.
Because you simulate it. Mm-hmm. And then there's a I forget which school it is. There's a bunch of researchers working on that right now, and they're having very little success, which is kind of sad.
Mm-hmm. No potatoes like in the Martian.
No, they're saying the soil is so acidic and toxic to that you'd have to really do a lot to it to get it to do what Mark Watney did with with the manure and the Martian soil.
Well, color me disappointed.
Yeah. So I think it's going to be largely hydroponic in terms of space farms, but I guess we'll see.
But it's good to know that at least before you go.
Yeah.
Like, and there's lots of water. Really it looks like there's plenty of water. So
there's plenty of water.
Nice solar energy.
So then Mark Watney didn't need to know the whole burn the rocket fuel to make the water part, and his soil wouldn't have worked in the first place. So really, it's going to be the exact opposite situation.
Yeah, it was funny. I heard one scientist say when they were interviewing Andy Weir that all he would have to do is bring some Martian soil inside, and the water would drip out of it.
Huh.
Yeah, interesting.
That's insane. Yeah, I guess so.
Yeah.
Well,
have to be very salty water, though.
Yes.
Yeah.
You'd need a good desalinator. We're now 10:05. Eric, did you have anything else you wanted to add about your view or what you're using with your right now with your while providing us the live views, or are you good?
I think I'm pretty good. Once we're done here, I'm probably going to continue the stream for a short while, but I'm actually going to go offline and start taking some offline video clips Because as I said before, then I'll be able to keep the raw data on the computer here, and I'll have better control over it that way.
Do you have a channel to which we could direct people if they wanted to continue looking?
Well, there's the Eric Briggs channel on YouTube, and I'll try and
I'll find it and just make sure it's not
Yeah,
Angry
make
Catfish Briggs. That's a different
make
person.
sure it's the right one.
It's not, yeah.
Hmm.
Let's see.
So that's about all I have to say.
Here.
Thank you, Eric.
Well, it's a great, yeah,
Thank
it's a
you.
great view. Thanks, Eric.
Thank you, and thank you everybody. So first of all, Eric, we really appreciate that you're able to offer the view when none of us other folks could really. So thank you for giving us your time for that. I believe I have your accurate one. It has a picture of the moon, so I'm going to assume that's you. So there's
That's me.
Eric's YouTube channel. If you want to watch it, I'll add it to the YouTube comment section as well in case anybody wants to continue. There you go. And thanks to like all of you who've been here as well. And I know Erin's not here anymore, but huge thanks to Erin for coming and talking to us about so much cool stuff that we didn't know about. And then Ryan, Chris, John, thanks again for not only now, but all the other times that you've helped out with RASC and doing all sorts of cool stuff about space. And Eric, finally, thank you for all the live views and for all of the in-depth knowledge that you hold with all this stuff. So I've had lots of fun with you guys tonight. Lots of fun with everybody in Zoom and on YouTube. Thank you everyone for joining. And I think that wraps up our week of Mars stuff. If you have more Mars questions, you have to wait 26 months. Sorry.
Well, you can see Mars until May, but it'll get pretty small and weak by then. But take advantage now the next few weeks and take good looks.
Yeah, and if you have any questions, definitely reach out to us on Twitter and everywhere.
All of them, all Ryan, Chris, and John all have social media. Ryan is Astro in Action. Chris is Astro Geo Guy.
Yep.
Got it right? Yes. And John has Learn to Stargaze. So you can find all of them on Instagram. You can find us and social media in general. And you can find RASC on social media too. Come and say hi. We don't bite. And we like to hear about what you've been up to as well. Thanks everyone for joining tonight, and we will see you all next time that we see you. John and I have a session on Thursday if you want to talk about what to see in space, so you can join us for that if you'd like. And then Chris and I will be back next week with Guinness
Out of this world records.
I'm excited.
will
So
be.
we've got those two coming up. Check out our website if you want to sign up, and we'll see you all next time. Bye, everybody.
Thanks, everybody. Keep looking
Thanks,
up.
everyone. Clear skies to you all.
Night.